And our final talk of the morning session is titled OFConnect, an open source OpenFlow networking library. And our presenters will be Deepa, Karnad, Dhurka, and Ramya Bolla from codechicks.org. I apologize.
My name is Deepa Karnad Dhurka. I'm co-presenting OFConnect today with Ramya Bolla. So OFConnect is a networking library. As it says, it's open source. It's primarily for OpenFlow. We built this project as part of CodeChicks. And CodeChicks, as some of us know, is a nonprofit organization based in the Bay Area, with chapters across the cities in the country and also now around the world. And it's doing an excellent job in providing a platform for women engineers to grow their skills in a very hands-on approach. So with that, I'll start the talk. The agenda today is, I'll just go over what OFConnect does. And then we'll go into design and architecture, and this is the part that I'll share with Ramya. Excuse me, Ramya. And then I'll go with the API and some screenshot examples, and if somebody wants to join in and help contribute, there'll be some pointers on how to get started. So here we see a very simple depiction of a rather simple SDN connection between a controller and a switch. And what you're seeing is in the blue box is the OpenFlow driver. And that essentially is what translates into a shared library that we have developed and called as OFConnect. CodeChicks has open sourced it. That's point number one. And we are adhering to a true OpenFlow implementation within the library. And the purpose of this is to provide an abstraction for OpenFlow, so it promotes quick development of new controllers and switches. I think a reference to this can be made to the owner's talk that was made yesterday, and it kind of demonstrates how abstracting OpenFlow or any such mechanisms into its own layer, into its own library, has benefits of very clean design and development for the rest of the controller and the switch. So just to give an example, just to demonstrate what exactly we have created here, we have the OpenFlow driver, which is designed into a shared library. Around that, we built unit test automation, which we are rather proud of and which helped us a lot in the course of the development of this project. The next bit is the Mulk controller. This is an open source C-based controller, which we used to integrate our library as proof of concept. And this was very interesting because we essentially had to take an existing working controller, tear it apart, and plug in our shared library into it and demonstrate the usability of the library. And that's essentially what gave us the entire SDN test framework that we are able to demo with. And with the documentation that completes what we have in the repos today. So these were some of the requirements functionally that drove the scope of the library. Primarily, the very first we have is that it should be able to be usable both by the controller and the switch. And then also pointing to the last one is something that takes away the onus of talking over the network out of the controller switch into the library. So any kind of wire protocols are hidden, the mechanisms of that are hidden inside this library. And the support for the protocol itself is OpenFlow, and the requirement is to be able to support multiple variants and versions of OpenFlow. In addition to this, we also went by another set of requirements, primarily for greater adoption of our library. And that mostly goes with platform independence and multi-language bindings. And another hard requirement that we placed on ourselves was to be able to create a full SDN demo so we know it's really usable and working. So a note on where we are today in terms of the repos. As part of phase 1, we got this part very strongly implemented, and we have the TCP and UDP, and the next step would be to introduce TLS into the library. We have a very extensible design that allows us to introduce new protocols more easily. We have also designed in being able to use this with the controller or the switch in terms of API that are reusable either way. As far as OF connections go, we have a very good starting point in terms of awareness of DPID and AUXID into the library. And in the subsequent phases, we intend to pull in a lot more of the OpenFlow protocol specifications into the library. But that's where we're headed next. Actually, I think I went back. Oops. Sorry about that. So yeah, a point I was trying to make was, in terms of the other requirements, actually we are way ahead of our targets. We have platform independence, and we have multi-language bindings in Java, Python, and natively it's developed in C. And a full SDN demo, some of the screenshots of which Ramya will be showing today. Okay. So a design goal that drove a lot of our decisions was to do with performance under scale. And this is where we wanted to introduce some level of complexity as a future objective of being able to handle a lot of scale. This picture actually demonstrates what we want to achieve. Here we have one controller driving multiple switches. And if we are to start with a number of switches like 1,000 per controller, and we are scaling all to the entire capacity of the number of auxiliary channels. Our target is to be able to handle about 256K connections, including all auxiliary channels as well. The other goals that we targeted for is to have a very generic framework, so any new RFC or any new standard that comes in as part of support for OpenFlow on the transport or the IP, TCP/IP stack, we should be able to add in a very straightforward way. And a common API, by which I mean the greatest intersection of API for both controller and switch. So here, this is a simple block diagram. We start with the API, and northbound are the SWIG bindings, which allows us to give Java and Python bindings as well. This is where the switch or the controller attaches itself to the library. And inside the library, we have two major components. One we call the net services, which is the different transport protocols. And the other is a thread management infrastructure that is able to handle as few or as many connections as the controller switch needs at that time. A quick run through of the API. This is the entirety of API we have. I can show you the basic stuff that we have is library init and free, and the device, every device is a connection between a controller and a switch. We are calling that the tuple, a device. And then we have channel setup and delete, and destroy also as a utility to delete a lot of channels at the same time. And then finally the send and receive, which is really a simple set of API to start with. So this is a sequence diagram for the OpenFlow channel setup. And there's a bit going on here, but let me point you to some of the highlights here. So we have OFConnect used by both the controller and the switch. And what you can notice here is all the socket socket mechanisms are hidden into the library, and none of that the controller of the switch needs to worry about. All it does is once it registers itself as a device which essentially tells the library which switch it wants to talk to, and then this controller waits for a channel to be created by the switch and accepts it. Now this is the part where as an enhancement we want to roll this into the library. At this point though, we having the controller and the switch do the OpenFlow setup part of it. Following that is this is a detail that kind of there's a learning of the DPID and aux ID that happens as a subsequent step. This is depicted by that, and then at the end is what we have is just the packet send and receive. That's when our channel is actually set up. So with that, I'll call Ramya to go over the next level of detail with the design and architecture that we have. Thank you.
So we had some design choices to make in the process of designing this library, and one of which was whether to use a static or a dynamic thread model. So, should we deploy n number of threads and, handle all the connections using those static threads or dynamically manage them? We chose to go with the dynamic thread model because, as you know, we need to scale a lot for 256K connections. At the same time, we need to perform well. So that's why we went with the dynamic thread model. And the other question was, to what extent should we process the OpenFlow packets within the library itself? We're doing a part of it now, but we plan to extend it further in the future. And the other question was whether to do a pole-based socket processing, which is using select or pole, or an event-based socket processing. Currently, we implemented it using pole-based socket processing, but we also plan to try out an event-based socket processing and see if it gives us a better performance, then we'll stick to it. So this is kind of, gives you an example of what Deepa was pointing out as to how we are providing a generic infrastructure to, add any new underlying protocols that will be used by OpenFlow. So if there is some new protocol that OpenFlow uses tomorrow, then we will be able to register new callbacks and we'll be good to go. So here's an example for TCP here, but the same way we should be able to add callbacks for IPv6 or TLS or any new protocol for that matter. This is one single thread administration block that we have in our thread library infrastructure. So basically every thread has a thread manager associated with it, which actually takes care of addition or deletion of socket FDs to that particular thread during session teardowns and session initiations. And at the same time, we have a pole thread utility that actually translates the the pole in and pole outs to their respective callbacks from the TCP and UDP layers based on the protocol that socket FD belongs to. And yeah, this actually gives a big picture. As I said, we are sticking to a dynamic model here. So as in when, I guess currently per thread, we have a capacity of 200 socket FDs. So, as in when we have new OpenFlow channels being connected, and if we exhaust the capacity of a particular thread, then we spawn a new thread administration block. And at the same time, we kind of do a load balancing here. That is, we don't necessarily add the new OpenFlow channel FDs to the immediate thread. So depending on, which thread has least number of FDs that are being processed right now based on the current thread load, we try to push it to the thread which has the least load currently. So that way we can get better performance. Okay, this is what it looks like inside, each thread. Each thread has a kind of a pole loop here, which constantly polls on its two pipes that are associated with it. So there's a control pipe that is responsible for any addition or deletion of FDs itself when every time we have a session creation or a session teardown. And we also have a data pipe that is responsible just for addition or deletion of the packet data itself. So at the same time, when the controller needs to send out some packets, it will communicate it through the API, and the API will add the packets to our data pipe, which will result in a pollen event on that particular pipe, and the corresponding callbacks registered for that particular channel will be triggered and the packet will be sent out. Similarly, the case with RX, and as I had mentioned, every time we create a new channel or delete it, we have new FDs being added or deleted into the control pipe. So this is our current test setup that we are using. Basically, we have used mininet to deploy an OpenFlow vSwitch, Open vSwitch, and we have, as Deepa had mentioned, we have integrated our OFConnect driver with the Mule controller. So we had to take out all the OpenFlow protocol part of it from the controller, and we had written some glue code to actually integrate our OFConnect driver to the controller, because we didn't have a new controller. I mean, we had to prototype it using the existing controllers today, which already have OpenFlow integrated in them. And so we use the default topology that mininet has, and with 2 hosts and 1 OpenFlow switch. And this is the kind of packets that we see going across between the controller and the switch. We see that there are hello requests being sent and responded, and there is a feature request reply, and there are echo request reply. So the echo request reply are kind of heartbeat messages that need to be sent constantly and responded to, so that the connection, just to let the switch know that the connection is up and running. And there are some packet end messages, for things. These are just some of the logs from our Mule controller. It just shows at what point it receives these OpenFlow messages, various messages. So every the library hands over these packets to the controller, and so the DP IDs are not actually set in the first hello message itself. So the DP ID is received at a much later point in the OpenFlow features reply message. So until that point, we kind of use a dummy DP ID to communicate with the controller, so that we have a similar mapping. And the moment we receive a features reply, we kind of change it to the actual DP ID that the message has. So these are just some of the learnings that we learned through this project. In order to provide platform independence, we chose to use glib as our library for developing our core infrastructure. So that way, we didn't have to worry about any platform independence stuff. And in order to export our API in multiple languages, so that it can bind with any controller or any switch written in any language, we have used Swig, and currently we provide support. We provide bindings in Java and Python apart from C. And we had actually gone through, we had to do extensive research to figure out what existing controller should we be using to actually prototype our driver. So, I mean, we had looked at Nox, POX, and multiple other controllers. So in the end, we decided to use Mule, as it was already in C, and we thought it would just make it easier for us to actually test out things in the beginning. So later on, we came up with the Swig binding, so we should be testing it with some other language controller in the future. And so as part of our future plans for this, since we've open sourced it, these are the things we plan to do. We plan to add a TLS we plan to add the TLS protocol awareness in the library, so that we can make the OpenFlow channels more secure. And we also would like to make it more aware of the OpenFlow protocol, OpenFlow packets itself, maybe even inspect the packets that are being sent as part of the OpenFlow data. And we also need to extensively test our library with in a large-scale deployment to handle 1K switches per controller and 256K connections per controller. So we plan to also profile it and also try and integrate it with maybe 1 or 2 other controllers and see how it performs in order to profile the library. This is kind of a summary. As we said, it's an OpenFlow networking library, and we have open sourced it with a GPL license. So anyone can join and contribute. So these are the repos that we are using. One is for the library itself, and other one is the Mule repo, where we have our library integrated with the Mule controller. That's about it. Thank you.
So we have plenty of time for questions, so I'm going to start out with a question of my own. I noticed that you mentioned at the beginning of the talk that you were proud of the tests. So could you tell us a little bit about the tests? Tests are always a big concern of mine when I'm working on a program, and so I'm always interested in hearing other people's approaches to them.
So in terms of tests, initially I talked about the automated unit testing. So I focused a lot on designing automated testing for the core infrastructure part of it, which was a thread management library. So right now the main focus of that is to make sure that it's pretty solid, because everything else kind of relies on that. In terms of SDN setup framework itself, we haven't yet automated that. That was more of a manual approach with the framework, from a controller to switch connectivity and a test bring up.
All right, thank you. Do we have other questions from the audience?
Hamel from Broadcom. I have 2 questions. First one, what do you do to verify the conformance of your implementation with the protocol spec? That's the first question. And second one, what kind of interop testing you have done with your implementation and other OpenFlow implementation?
So let me answer with the degree of OF awareness that the library has right now is to the extent of understanding the DPID and the aux ID. So at this point, I can say it is pretty version agnostic. But going forward, we want to be able to have awareness of different versions of OpenFlow, and that has not yet been designed. It's the next subsequent phases that we are planning. In terms of interoperability, we have plans for testing with actual OpenFlow switches, and actually trying and integrating this with a switch as well. So interoperability in terms of library linking versus also different versions of OpenFlow, negotiations at either end. So those are some of the things we'll be exploring as we develop this further.
Thank you.
More questions?
Hi, my name is Vikram from Convoy Technologies. I have a question. So you said you use Mule controller, right? What was inherently it was using as a driver for OpenFlow? And do you see any value addition by using OFConnect, or?
It was tightly integrated. It wasn't as a separate library or abstraction. It was written as part of the code, which is the part we had to kind of separate out and then plug in our shared library. In terms of performance, we haven't yet gone to the point where we can test performance with the library. But what we're hoping to achieve with this is easier integration. And if whenever OpenFlow adds a new feature, it can be developed as part of this open source library, and then Mool development doesn't really have to worry about it so much going forward. So those are the kind of benefits we are looking at, more than actually improving performance for that kind of an integration.
Anybody else? All right, let's thank our speakers.